All right, Huskies, now it's time to put our hands together and get some stuff done when it comes to doing limits. All right, this calculus thing that we've been talking about over the last day or so is now really going to start coming into its own. And here's the deal about math. Math from this point and forward that you're going to be really talking about is that they're going to generate new kinds of math that come up, but they're not generating them just because they think they should. It's because they fit into the patterns that we've been discussing when it comes to math in general. And that means that if you come up with something that you're going to say works in terms of a mathematical sense, you've got to make sure that it fits some serious criteria. Math teachers are very interested in what we refer to as closure. Okay. You ever break up with a math teacher, they'll make sure that they close it really well. That's because we like about closure. Now, what I mean by that is we don't like to have mathematics that have an opening inside of them, something that isn't defined in per se. So when we say we discuss something like calculus, we want to make sure that it's got all the ideas in terms of its closure. First off, do all the operators work on calculus or in terms of limits in general? That's a good question. How do you actually go about finding a limit, or how do you find some kind of a value for a limit? There's rules and ideas that pertain to this. You might also think about properties. The properties that you've been discussing in your math have all been kind of set in stone, like the addition property of equality and multiplication property. Do those properties actually apply to limits as well too? And we really think about these things all the time. When we come up with a brand new kind of idea in mathematics, we got to make sure that we close all the ideas and that all the ideas work. Now, for instance, in some particular regards, like in linear algebra, we may talk about matrices, and matrices have a gap in them. They're not closed in terms of division. They just don't work. So we have to look at and explore all these new different kinds of mathematical ideas and make sure that all the pieces of them work so that we can keep the same dogma, I guess, is what you might say about math going along. Now, the first one we're going to say is that we really discussed this 90% rule and the 10% rule. And for the most part, you've been probably relying on your teachers to tell you, yeah, this is just the way you do it. But as we get further down the line, you're going to want to make sure that it's acceptable to do what you do. So why is the 90% rule, where you just use plug it in kind of mathematics, why does it work? Well, here's some definitions or properties that help you understand why those limits work the way that they do when you just plug them in for the 90% rule. So here's kind of like a basic explanation or definition of why that is. Now, first property that they state is that if you take the limit of x as x approaches a, then that turns out to be just a in its own right. Now, what are they really saying here? The key is to remind yourself that where that x is at is really meaning f of x. And if they're saying if f of x is equal to x, then that must mean that that's a graph, or better yet, of y equals x, a graph of a diagonal line that would be graphed as such. Now, what they're saying is that if you picked any domain on that particular deal, say I picked over here the number 4 on the domain, if I went up to that f of x and then over to the y to evaluate the limit, it would be at 4 as well too. So this particular property is basically saying that if you take the limit of a variable, you end up with the domain that you were going to plug in. That's what that basic idea is. Now, it wouldn't matter if the line was f of x is equal to x, or if it was 2x or whatever. It blows down to the idea that you plug in the domain and you evaluate the variable as it comes out the other side. Now, the other one, the one next door to this, is the limit of a constant. What if you took the limit of a constant, say like the number 5? Like you're saying, hey, I want you to find the limit of 5 as x approaches, I don't know, 2. Well, the answer to this is 5. And the reason behind that is because we know that that f of x that you're looking at right there is f of x equals 5, and that is just a horizontal line at 5. And no matter which domain you pick going along that deal, whatever it's 2 or if it's 10 or whatever, it is going to give you a range answer of 5. And that's why a constant, if you take a limit of it, it is a constant. All right. Now, the reason now you're probably like, okay, those two properties make a lot of sense why they do that. Now, the key is that once you make these properties, you can actually start to make more complicated statements. As such, the limit as x approaches 5 of 12 plus x. Well, if you can see the limits of the individual concepts, then this plus sign is really just an addition between two separate limits. So it's okay to write a set of limits as separate limits, as the addition of both of them individually. And now I've broken it down into two individual properties that are based on the two that we have above. The limit of 12 as it approaches 5 is 12, and the limit of x as it approaches 5 is 5, and that answer is 17. And what I'm really doing here is laying down the idea that a constant or a variable can be actually evaluated in terms of its individual limit. And regardless of operators, limits work on the same operators as anything else. They work with a subtraction, they work with addition, they work with, over here, check this out, the limit as x approaches 2 of 2x minus the limit as x approaches 2 of 5. This whole idea times the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. And you ultimately get this broken down into two individual kinds of ideas of properties. You plug 2 into this one, you'd end up with 4. You'd plug 2 into this, so it doesn't plug in, it's 5. So that answer would be -1. And this one on this side, you plug it in, you get 2 plus 3, and you get 5. And you'd multiply those two answers together and get an answer of -5. It is because of those two prior properties that the 90% rule works. It's basically stating that this is a plug and chug kind of idea, mainly because as you break down the limits into their fundamental pieces, you're really not doing anything to them that would be non-mathematical anyways, okay? Non-algebra sense kind of idea. Say same kind of idea here. Say I wanted to find the limit as x approaches -2 of 4x squared plus the limit as x approaches -2 of 5, and then take the whole thing and raise it to the 1/2 power. It is the same deal. And so what's really the cool part about this is that you have so much cool algebra in your background that ultimately these kinds of questions, that would be 16 plus 5, and then I take the square root of that, which would be the square root of 21, means that you really got a lot in your repertoire that you can use to help you figure it out. Same kind of idea here. If you're not seeing anything that is going to cause the limit to be something unsuccessful, like a dividing by 0 or infinity or such, then the 90% rule is valid, meaning that you can just take the value and plug it in wherever you see x and evaluate the question. This one happens to be 4 times 27 plus 2 times 9 minus 6 times 3 and plus 5. And in an end result, you end up with like 77 for this answer. And that's what that limit would be. Now, as proof that that is going to work, I'm going to show you, like say this limit right here, specifically, that if I plugged it into my calculator and plugged in, hey, 4x to the 3rd power, and then I also plugged in plus 2x to the 2nd power, and then I did minus 6x, and then I added 5, but not necessarily just plugged values in. What if I wanted to table set this and actually look at it really close to the number 3? So I'm going to go, hey, started at 3. I'm going to do 100th on either side of it. And if I tablize this, you'll see, ooh, I got the wrong answer, that the answer is approaching 113. Ooh, did I do that wrong? Let me see. 4x to the third plus 2x minus 6x plus 5. Hey, calculators don't lie. This answer must be getting really, really super close to, that's a good reason to check your work here, 113 is what it would actually be getting to. So I'm going to change my answer right here and scratch out 77, 113. If you tried numbers that were closer than even 100, you'd see that they're both approaching that particular value. So if I maybe the table set, we'll go down to a thousandth. Let's do one more extra 0 in there. Something like that. And then I tabled it starting at 3. Oops, not there. Delete. I'm going to go up here to start it at 3. You'll notice that the numbers will get incredibly close to 113. Okay, we're getting closer and closer to that. That's what that limit basically works. Now, the rule here is, as I say, a 90% rule. You plug in 90% of the time, it'll give you the job, get the job done. It's when you run into things that you've got to be able to adjust and figure out, oh man, the 90% rule isn't going to work. Now, if I plugged in -2 into this question here, is it going to give me a valid answer if I really wanted it? So it's going to be something upstairs of 3 times -2, and the bottom's going to be -2 minus 4. That's -6 over -6. Hey, the answer to that is 1. And I'm just going to check on my calculator real quick, make sure that that answer does seem to make sense approaching that particular idea. So let's see here, 3x and then divided by, and you can always tablize any limit to see whether or not you're relatively close to the answer that you're supposed to get. Close that thing. And then I'm going to table set this to start at the number -2. And again, go by very small increments. In my table, that thing looks like it's getting really close to 1. Okay, so far, 90% rule is like a gift. You're like, yes, 90% of the time, I'm going to get an A. And then there's that 10% rule that ends up making you fall flat on your face. What do you do if something goes wrong? Now, the reason I put a 10% rule on this one is because I can recognize that as soon as I plug in a value of 3, this denominator will turn out to be 0. And that is an undefined kind of idea. And you're like, I can't really say that the limit is undefined. Now remember, limits either have an answer or they don't exist. It's not like you're saying that it's undefined. As soon as you get zeros on the bottom, this is kind of a highlight film saying, hey, you better go check me out. There's other stuff going on. Trigger the 10% rule. Now, the 10% rule has some ideas inside of it that might help you get to an answer that looks better. And one of those ones that you might try would be to factor it. Okay, we learned factoring on purpose, and that is because you wanted to learn how to do calculus and do calculus well. So I'm going to factor each one of those. Now, the bottom one is a difference of squares, x plus 3 and x minus 3, and you're like, okay, that's doable. The top is a perfect square trinomial. And if you have to make the big X, then that's a default here. That would be an X minus 3 and an X plus 2 that would generate right here a -3 and a +2, and there's your two values. Now, the reason why you factored is you are hoping for a cancellation. And if a cancellation does take place, you can get rid of that concept and take the resulting answer and apply the limit again. And so once you've applied a 10% rule on it, you try and do a 90% rule again and plug it back in. And now you've made it so that the limit doesn't become an unnecessary answer. This answer turns out to be 5/6, and it turns out to be 5/6 is the answer. If you wanted to evaluate that, now 5/6, let's just decimalize that just so you can get an idea to see how that would turn out on your calculator. I'm going to quit on this. Go 5 divided by 6. And an answer is 0.833 repeating. Now I'm going to put this one in my y equals just to show you how we're going to evaluate this answer. and that would be the top guy. I have to go back to the original one. X squared minus x, and this is where your calculator, the table, can start to actually mess with you if you're not careful. You got to do the algebra. That's why you learned it. Divided by, and on the bottom, x squared minus 9. And I'm going to go to my table set the answer to be at 3, and again, very small increments around 3 to see what the table says. And you'll notice that at 3, it doesn't have an answer, but that doesn't mean that the limit doesn't exist. Look at what the numbers are getting really close to. They're getting very close to 5, 6, and it's 5, 6 on both the left and the right-hand side. It's not like they disagree. So you can't just plug them in all the time. Sometimes you have to look for some other 10% rule. Now, I've come up with a factor it kind of question, and this one right down here, number 7, is one that works that same way. You can see it happening right away. You're just like, oh man, 10% rule. And the 10% rule kicks on, and you need to factor it. Now, try it right now. Factor this question. See if there are any cancellations, and if there are, cancel them and retake the limit. I'm going to pause and then show you the answer. And there you go. That's what we're basically looking at right here. So first off, I took that trinomial and the binomial, factored. The bottom doesn't need anything. The top actually factored to 2x plus 3 and x minus 5. X minus 5's cancel. And then I reevaluate the limit with the leftover simplified value of what f of x is, and it generates an answer of 13. So the 10% rule is a way to help you simplify the idea before you try to apply the limit. Now, there are several things that we're going to see that the 10% rule can get you engaged in. For instance, number 8, I'm going to come back to this question. You can definitely see that the 0 on the bottom is going to cause a problem. But I'm going to go to number 9 first because this problem's a little bit more doable in terms of algebra, and then we'll come back to number 8 and try it together. Again, a 9 in here generates a 0, and even a 9 up above generates a 0 over 0 situation. This is a dead giveaway that the 10% rule is in place. Now, factoring it won't get you anywhere at all. So what we're going to do with this one is another technique, and it's going to seem out of sorts. In terms of calculus, there are a lot of rules that we say in algebra that we don't, that we say are no-nos, or you just do it a certain way. In calculus, you have to find ways to manipulate things in all different kinds of ideas, and equivalence means equivalence in that regard. If it's something you normally wouldn't do in algebra, as long as it's an equivalence, it's a reasonable concept. So what we're going to do here is we're going to conjugate this, but instead of conjugating the denominator, which we've always done in algebra, we are going to conjugate the numerator. And I'm going to put the square root of x plus 3 on the top and the bottom. Now this is a little bit different. We haven't seen a conjugated numerator before. But my point is that you're going to end up with an equivalence. And it won't matter what the standard idea is, as long as what you get in the end is an equivalent deal. Now, I'll have to FOIL these, and since you're using conjugates, front times front will end up being just x, back times back will be minus 9, and the inside outside, which would have been a negative 3 square root of x and a positive 3 square root of x, since you're doing a conjugate, this will end up being canceled. You'll end up getting a cancellation there. Now, the numerator turned out to be x minus 9, but the bottom is still going to end up being x minus 9 times the square root of x plus 3. Now, there's a reason why I'm not distributing that, and that is because this numerator broke down to be just x minus 9. And if that's the case, then these two concepts, or binomials, would cancel each other, and you'd be left with, and that's not right, not 0, 1 over the square root of x plus 3. Now, you're probably asking, did that make it any better? I'd have to conjugate it again, and it'd go right back to the other thing. But before we conjugate it again, did it fix the limit as x approached 9? And the answer to that is yeah, because the square root of 9 is 3, and 3 plus 3 is 6, and the answer to the limit is a sixth. And that's what we were really trying to answer, was the limit, and not just trying to go back and forth in terms of algebra. I just found an equivalence. This idea right here is equivalent to this original one right here, just written in a different way, and it works nicer with the limit. So a conjugating of a numerator is going to be a really good deal. So I'm going to put that up there as a possible choice too. I'll put here, conjugate a numerator. It's a very easy thing to do, and it can be very, very helpful. Now, sometimes conjugating a numerator can really kind of be a bummer, specifically because you might be dealing with a rather difficult square root, and trying to factor it or put it in there, it can be a little bit kind of a bummer. So I'm going to do this one conjugated out. You kind of see what I'm going to end up doing. Remember that you set up a conjugate specifically to make a difference of squares. And that difference of squares ends up making the O and I of FOIL disappear. You get that -4 and that +4. Well, man, those two are gone. So it's really an F that's going to be done here. Square root times the square root. That'll actually turn out to be 16 plus x because you're doing two square roots. And then you would do the last functions right here, which would be a minus 16. And the numerator in this case turns out to be really slick, is just x. Now the bottom tends to be a much uglier deal, and that's really x times the square root of 16 plus x, that's all underneath its root, plus 4. And I'm not distributing that, and I'm not doing it on purpose. The reason behind that is because sometimes if you leave these things out, they tend to eliminate themselves in terms of a cancellation from top to bottom. If you get a good cancellation, you can make some stuff go away. This is 1 over the square root of 16 plus x plus 4. And now if I go ahead and I apply my limit as x approaches 0, did it fix the limit? Well, 16 plus 0 is 16. The square root of 16 is 4. 4 plus 4 is 8. And the answer for the limit is an eighth. And that is what the answer would turn out to be using a conjugated numerator. Now, guys, the only way to get good at 8 and 9 is a little bit of practice. You got to try. So get after it. Try a couple of them on your own. See if you can conjugate them. Now, another technique that you might see in terms of using a 10% rule, you can see it's 10% because it ruins this one, and it ruins that one too as well. You get 0 over 0, is a common denominator deal. And I'm going to write that this x plus 4 minus 1/4 on the top divided by x over 1. I'm writing it as x over 1 because it's more of a complex fraction. That this guy right here needs a 4 top and bottom. Do you remember doing this in algebra 1 and a little bit in algebra 2? Of course you do. This one needs an x plus 4 top and bottom so that I can get a common denominator out of it. Now I'm going to push this down just a little bit so that we can get some more room in here and see what we end up getting as a numerator. Follow along with me. That's a 4 minus all of the stuff up there. So it's 4 minus x minus 4, because I had to distribute the x, divided by 4 times x plus 4. I'm not distributing it on purpose, divided by x over 1. So a little complex fraction. 4 minus 4 makes that just a negative x up above. So we've got a negative x. And if I invert this one and multiply, I'm just going to kind of put it right here in its own little ghostly form, 1 over x. If I inverted and multiplied, would that x and that x cancel each other? Well, of course it would. You'd end up with -1 on the top because this x and this x cancel all over 4 times x plus 4. Now, all I've done is create a new equivalence for this original complex fraction. Does the limit now work on that equivalence as I approach 0? 0 in there would be 0 plus 4 is 4. 4 times that is 4. Answer, -1/16. And that would be the answer to the limit. So in a lot of regards, these limit questions that are based on the 10% rule are really only algebra problems. And they're seeing whether or not you deserve to be in calculus because you know how to do algebra. So I'm going to, again, up here in my 10% rule, I'll put a third rule here. 3 things you should really try: factor it, conjugate a numerator, or make it a common denominator. And see if you can write it out. I can't spell. Common it's a B. Denominator. Okay. Common bottom. Oh, man. You guys are making fun of me now. I know it. Please don't. It'll hurt my feelings. Okay. Now, in terms of questions that you might end up seeing in the future, they may end up giving you an f of x that is a piecewise. And a piecewise question is really not that hard. We just got to remember that when we're talking about piecewise, what we really care about is, does the left and the right, do they communicate with each other and decide that they give the same answer? Now, I'm going to graph each one of these two just so you can get an idea of what's going on. They tend to have most of their stuff happening in the upper right-hand quadrant. So I'm going to make this a little bit bigger in the first quadrant. And I'm going to graph each one. So here's the value of 2 right here. That's the one that we really care about. And let's see what kind of numbers we would get. Now, I'm going to do the bottom one first because that's all the numbers that are greater than 2. And it is a line, is what it is. So it would start at 1. And it would go up 3 and over 1. 1, 2, 3 over 1. We're not there yet. 1, 2, 3 over 1. Okay. Now this would be a solid dot right here. And it would go 1, 2, 3 over 1. And then so forth. And this is what the line would look like on that far side. Inclusive being that it's solid here because it is got the bar there. And that graph only exists on the right-hand side of 2. Now this one happens to be a parabola. I don't know if you need to remember a whole lot about parabolas, but 1, 2, 3, 4, 5, that's where that one needs to intersect the y-axis at 0. And if you plugged in a couple of numbers, you can generate what the other ones would be. 1 would generate 7, 2, 3, 4, 5, 6, 7. And 2 would end up generating 9. So 7, 8, 9. 1, 2, 3. 1 would be 6, excuse me. 1 would be 6. 1 would be 6. 2 would be 9. 6, 7, 8, 9. And it'd be an open circle right there because it doesn't quite make it there. So this graph would look something like that. Okay. Now let's answer the question about whether or not the left and the right agree. Answer from the left, as you were coming into 2, it'd say the answer is headed towards 9. But if I was coming in from the right, he would disagree on his roller coaster. He'd be like, nah, I'm sorry. I'm getting really close to 7. And the answer for the limit in that case would be, it does not exist. So a picture really does make a lot of sense in that particular regard when you're talking about piecewise. Is the picture necessary? Not really. If you really want to think about the idea that this particular part right there is really saying left, and this one is saying right, you could evaluate the limit based on just the left and right decisions and decide what the limit's supposed to be if they agree. So you really could use a 90% rule kind of plug-in kind of idea. Here's an example. Do I really need to graph a parabola and a cubic to decide whether or not 2 is going to be a good deal? Now, the only reason why I'm going to check 2 is because 2 seems like the only likely place that this would be disjoint. The other 2 graphs, which are a parabola and an N-shaped one, they're continuous. And they would work on left and rights of whatever domains you were talking about. It's this 2 of whether or not they're connected to one another. And that could be the discontinuity. So what does the left say about the whole idea? Well, the left-hand guy, or 2 approaching 2 from the left-hand side, would generate an answer that came out of this deal. And it would get answers of, and it's a 90% rule, nothing special about it. 2 in there would be squared as 4 plus n would be give you an answer of 10. And then the right-hand limit, as x was approaching 2 from the right-hand side, would generate stuff from this one. And if I plugged in 2, I'd get 8. 2 to the third power is 8 plus 2 is 10. And here's a quick synopsis. do the left and the right limits coincide? And the answer is yes. They agree that the answer is going to be 10 at that location. It's because they agree, and they actually connect at that location. Now, a left and a right can easily be identified by a less than or a greater than. What does this particular one mean? Now remember that we're talking about a limit, and the limit as it probably approaches 4 of this f of x. And if you're going to talk about the left and the right, you're really going to talk about this guy right here. If you're not equal to 4, you're either on the left of 4 or you're on the right of 4. And this happens to be a left and a right concept at exactly the same time. This guy down below, he is not left or right of 4. He is 4. What's happening at 4? And so that part right there is really a question of, if I was being asked of what is f of 4, that would be 7. But if I was being asked the limit as it approaches 4, I would really be triggering the upper section and the upper section only. Now, I got a problem with the upper section. As soon as I try the 90% rule to plug it in, you can automatically go, ew, it doesn't work. It doesn't plug in there correctly. So I'd have to go to one of my 10% rule chances to figure it out. Should I factor it? Should I conjugate it? Should I find common denominators and make it so it's simplified? Well, it seems to make sense that this is probably a factor question. And what's really going to challenge you is whether or not you're a good factor or not. The bottom is x minus 4, no big deals, but do you remember how to factor a cubic, especially a difference of cubes? It happens to fall into a rule that it's a minus b times a squared plus ab plus b squared. And there was a rule based on that from Algebra 2. So this top part would be x minus 4, because that's 64 is the cubed root of that. So I cube root each one. That gives you the binomial. And then I always remember this part as square multiply square, and it gives you the numbers that go on the inside. And it happens to only have one negative in it ever. Now, if the binomial is negative, these are both plus. If it was a sum, this would be plus, and this one becomes the negative. Now, the reason why I did that is because cha-ching, look at that. 2 of them cancel each other. And now we're down to finding the limit as it approaches 4 of the remainder piece. And if I was to do that, I would end up with an answer of 48. And that's 16 plus 16 plus 16 is 48, right? And that would be the limit. Please note, the answer to this guy, if it was a limit, would be 48. But if you were trying to find out what 4 was in terms of algebra, you would trigger the bottom guy and the answer would be 7. So be very careful that you're clear what you're asking. Are you asking for a limit or are you asking for an evaluation? Okay, both things have different characteristics associated with them. The left and the right guy both agree the answer is getting close to 48. All right. If you have any questions based on these, please don't hesitate to ask your prospective teacher. And again, don't make fun of me for not being able to spell the word denominator. I can do it now. I'm pretty sure I could. Oh, I don't want to try. I'm scared. But have a great day, guys. And hopefully you're learning something out of all this calculus that we're getting. And it'll be really helpful for you in the future.